All right, chemistry. Let's get this 9B section review done. Number one, the reaction that occurs when iron rusts is given below. Here it is, number one. 4Fe, which is a solid, plus 3 O2s, which is a gas. And of course, there's a lot of other things, catalysts and stuff involved in reaction. Water, for example, a little bit of acid or base can facilitate this. But if you just the basic reaction, it produces two Fe2O3s. Solid rust. And we've already balanced it, so because we did that last unit, what we're asking for this time is some numbers, calculations, how many moles of rust can be produced from 3.2 moles of iron metal. 3.2 moles of iron metal. 3.2 moles there of iron metal, and we want to know how much rust is going to be produced. How many moles of rust? Yeah. So we want to know, what is this? Well, the balanced chemical equation tells us that 4 of those will make 2 of those, or which is a ratio of half. So 3.2 moles of iron should make half as many moles of iron oxide, which is 1.6, right? That's the answer. Okay, let's do it formally because some of you may not see the mathematics of that and you like a nice, neat, organized system to solve these problems. We call it the factor label method. We ask the right question: how many moles of Fe2O3 will be produced from or equal to 3.2 moles of Fe? That's the question. How many moles of iron oxide is going to be produced from 3.2 moles of iron? When I know, that's the times, I know this. These two things are equal. And of course, if the numerator and the denominator are equal quantities of something, in algebra, that means it's multiplying times the number 1. Well, from the equation, I know this. I know 4 moles of iron makes 2 moles of iron oxide. We just got to decide which one do we put on the top, which one do we put on the bottom. We're trying to get rid of this unit label, so we want to factor that. That should be the unit we put on the bottom. Moles Fe. Well, that means the moles of iron oxide then must go on the top. Fe2O3. What is the numbers that go there to make these quantities equal? Well, 2 moles of this makes or is made from 4 moles of iron. And there you see the ratio is 1/2 or 2/4. And how do we solve mathematically? We multiply 3.2, which is a numerator. It's over 1. We multiply that times 2, divide by 4, which is, of course, half as much. 1.6 moles. The only unit label that's left, because we've factored that one out, the only unit label that's left is moles Fe2O3. Mole Fe2O3. There. That's the answer to 1A. B. How many moles of oxygen will be consumed in this process? You know, this is the kind of stuff that chemical engineers would be concerned with is how much of one material it has to be provided to react with so much of another material so that we get a particular product in a certain quantity. Not that chemical engineers are probably trying to make rust, but actually this is the stuff, rust, is what we used in that thermite reaction. A really hot, bright, flashy thing. And they use it to weld things many times. So the question now is, how many moles of oxygen would be used from how many moles of oxygen will be consumed in this process? Well, it's equal to the same amount of iron, 3.2 moles of iron. So that's our question. How many moles of oxygen equals 3.2 moles of iron? Now, some of you already saw it. Well, I know 4 moles of that requires 3 moles of oxygen to burn it, to rust it. And maybe you could do that in your head then. 3/4 as much oxygen will be consumed as iron. Or because sometimes we get things flipped over in our head and we multiply times 4/3 instead of times 3/4. Anyway, I admittedly like to see the factors, labels all factored out like they're supposed to be. We could put this. Moles of iron has to go on the bottom again. 4 moles of iron on the bottom. Now the number 4 doesn't cancel, just the unit label. And how many moles of, we're asking for oxygen. How many moles of oxygen? We look at the balanced equation. It's 3 moles of oxygen. So we take 3.2 times 3, divide by 4, and what do we get? 2.4 moles of oxygen. C. Both CSI, yes, and C as in letter C. What mass of iron metal is needed to form 100 grams of rust? A little different question this time. What mass, how many grams? Now we're in grams, not moles. But that's okay. We can convert from grams to moles because of the mass on the periodic chart. How many mass of iron metal needed to form 100 grams of rust? How many grams of iron is needed to form 100 grams of rust, which is the Fe2O3. Now I can't go to the I can't use these numbers in the balanced equations to deal with grams because iron doesn't have as much mass as iron oxide. Iron oxide's got 2 irons and 3 oxygens on board. Each one of those units is going to weigh a lot more. So we have to compensate for that. You know, I'm going to move that whole thing over just a little bit. I'm going to need the space. C, the question, how many grams of iron is going to be needed to make 100 grams of rust, iron 2 oxide? Well, then in order to use the balanced equation, I have to have moles. So the first thing is we take our mass and we convert it to moles. In this case, we want grams of iron oxide to be factored out, so we want grams of iron oxide on the bottom. Moles of iron oxide on the top. Well, a mole of iron oxide, how do you know how many grams 1 mole is? Because these two things have to be equal, because that way the factor is 1. The only thing we're changing is the unit label. How many? 159.7. 159.7 grams. Well, where did I get that number? Please tell me you know. Very good, very good, very good. Iron is 56, 55.5 something. Take that times 2. Oxygen is 16. Take that times 3. So you get 110 something from that. 55 times 2, right? You get 16 times 3 is 48. Anyway, add all that together, you get 159.7. Okay, I need that space. 159.7 from adding the mass off of the periodic chart. Add those masses together, 2 irons and 3 oxygens. Okay, we've got rid of the unit grams of iron oxide. Now, we have the unit moles of iron oxide, but we want grams of iron. So we're going to have moles of iron, and then we can change it back to grams of iron. So moles is converted to moles. In this case, it's moles of one substance, the iron oxide, is converted to moles of iron. How do you do that? Well, where do we get the ratio of moles of iron to moles of iron oxide? From the balanced equation. 2 of those makes made from 4 of those. So I put moles of iron oxide on the bottom, 2 moles of iron oxide on the bottom, and 4 moles of iron goes on top. Some of you might have just recognized, oh, well, you need 4 times as many atoms of iron oxide as you get units of iron 2 oxide. 4 moles, 4 units or atoms of iron to make 2 units of iron oxide. Anyway, we cancel that unit, moles of Fe2O3, and we're left with the moles of iron there. We got one more step because we didn't ask for moles of iron. We want grams of iron. Not how many atoms, but how heavy would they be? Because when we're in their lab, of course, we can't count the atoms. We have to measure their mass. So, using the same factor label method, these long problems, that factor label method comes in handy. Moles of iron goes on the bottom. 1 mole of iron, does it have to be 4 moles of iron on the bottom? No. We're not canceling the numbers, we're just canceling the unit label. Moles of iron oxide. What is a mole of iron oxide in grams of iron? I said that wrong. Moles of iron in grams of iron. Well, once again, we look at the periodic chart. The periodic chart tells us how much mass in AMUs each atom is. It also tells us how much mass each mole of iron is in grams. 55.85. So 55.85 grams of iron is a mole. Mole of iron cancels with mole of iron. The only unit label we have left is grams of iron. This is probably the hardest problem that we do in Chem 1, just because it's so long. It's so many steps. The first thing we do, we change the mass we're given to moles, because then we can use the balanced equation. We change moles of that substance to moles of the other substance from the simple stoichiometric ratio, the coefficients in the equation. And then we change moles to mass of, in this case, iron. Some people call these mass problems. You're converting a mass of one substance, Fe2O3, into the mass of the other substance. But in the process, you have to go through the moles. So it's really a mass to mole to mass problem. Or for short, mass to mass problem. And the final answer, 69.94 grams of iron. Do you get, please show all this work. Don't just write the answer down. Yeah, because the process is the important part. You know how to solve the problem. Mass of iron oxide changed to moles of iron oxide, changes to moles of iron, changes to mass of iron. Multiply everything on the top. 100 times 1 times 4 times 55.85. Divide by everything on the bottom. Divide by 159.7. Divide by 2. And you get 69.94. Let's pause that for a moment. Let me erase my board. And letter D. How many molecules of oxygen will be needed to react with 50 grams of iron metal? D. How many molecules? Molecules instead of moles. We don't typically do this kind of detail work. We usually just leave it at moles, but we'll convert it to molecules of oxygen. O2. To react with 50 grams of iron metal. 50 grams iron. Change to moles. A mole of iron. Notice the moles of iron's on the top, 55.85 grams of iron on the bottom. The last time we used it, we had the 55.85 on the top. Well, we're factoring that label, grams of iron. In the problem before, we wanted the label, grams of iron, on the top. We were factoring the other label. We were factoring out the mole. But we want to know oxygen. Well, from the balanced equation, which I've erased, but you have it up above, we know that 4 moles of iron for every 3 moles of oxygen. 3 mole O2. We factor out that label, and we're one more step. We have moles of oxygen, but we want molecules of oxygen. How many molecules of oxygen will there be? Well, moles of oxygen on the bottom. And how many molecules are in a mole? How many anything is in a mole? How many things are in a dozen? 12 in a gross, 144. In 2 gross, 288. In a mole, 6.02 times 10 to the 23rd. There, we got rid of the unit moles of oxygen, and we're left with the unit, which I don't have room to put it on here, but this is molecules. Molecules of oxygen. Our answer then will be something with the unit label molecules of oxygen. Put all those numbers in your calculator. 4.04 times 10 to the 23rd. Molecules of oxygen. If you want to know what it looks like to put all those numbers in the calculator, because you do need to know how to punch this in, let me show you that. We would take 50 on the top, 50 times 3 times the number 6.02 times 10 to the 23rd. Sometimes people have trouble putting that in the calculator. Times 6.02, enter exponent EE. 23 equals there. So far, our answer is 9.03 times 10, that's what the exponent means, times 10 to the 25th power. Oh, but we have to divide by the stuff on the bottom. Divide by 55.85. And then also divide by 4. It's on the bottom. Divide by 4 equals 4.042076991943, of course, times 10 to the 23rd. But we don't put all those numbers down. That is not a good answer. If you wrote all those significant figures down, that would be lying. You don't know that many things. We only know 3 of the numbers. Technically, I see that I made a mistake. This should have been written as 50.0. That would give you 3 significant figures. There's 4. These are exact numbers, so you don't have to count them as significant figures. And we used 3 significant figures in Avogadro's number. So we can keep 3 significant figures in our answers, and we did. Number 2. Use the reaction in question 1 to answer these. The reaction number 2. 2A. The reaction, the same thing. 4 Fe plus 3O2 yields 2 Fe2O3s. Okay, now we're going to use that equation to answer this question. If 200 grams of iron reacts fully with oxygen, what's the theoretical yield of Fe2O3? They're just using a different word. Theoretical yield of Fe2O3. So the question just looks different. What is the mass? How many grams? Theoretical yield. Theoretically, when we do this calculation, this is how much stuff we should have made. How many grams of iron 2 oxide will be made from? Yeah, theoretical yield of iron 2 oxide. Theoretical yield of iron 2 oxide, which is how many grams of iron 2 oxide, of Fe2O3. By the way, that's not iron 2 oxide. That's iron 3 oxide. The reason is because oxygen is a -2, iron is a +3, and that way +6 and -6 make a 0. So the name of this compound is iron 3 oxide. I've always done that. I always say the subscript as the name, but the subscript is not part of the name. It's the charge or the oxidation number on it. So that's iron 3 oxide. How many grams of iron 3 oxide would be made from? 200 grams of iron. 200.0 grams. I don't know why. That's another bad habit I have. Because if they give us 0.0, that means that they have actually measured this. So it's part of the number of significant figures. 200.0. That's different than 200. That's 4 significant figures. So we want to know how many grams of iron oxide, iron 3 oxide, would be made from 200 grams of iron. Well, we have to have moles. We have to change mass to mole to mole to mass. It's another mass problem. We'll do this. Get rid of the unit grams. It'll be 55.85 on the bottom. Grams of iron. That is 1 mole. Got rid of the unit grams of iron. We want to get rid of the unit moles of iron. We want moles of iron oxide. Well, from the balanced equation up above, you saw that 4 moles of iron is needed to make 2 moles of iron oxide. factored out that label. And the last step, we want moles of iron 2 oxide on the bottom, so it'll factor whatever's on the top. The unit on the top needs to be on the bottom for the next step. Fe2O3, hard to write small, Fe2O3, and how many grams is a mole of Fe2O3? Well, we had this before, 159.7, wasn't it? Yes. 159.7 grams of Fe2O3. The unit label moles of Fe2O3 cancels, and the only unit label we have left is grams of Fe2O3. Ta-da! We factored out everything we didn't want, and we're left with the unit label we do want. Put all that in, and it comes up 285.9 grams of Fe2O3. 285.9 grams Fe2O3. Show your work. Show the calculation. Don't just write the answer down. All right. This is the theoretical yield. Part B of number 2 asks this question. What's the actual yield is 252.7. So, in other words, you actually went to the lab or maybe in the factory, chemical manufacturing plant, and the actual yield was not what we predicted it would be, 252.7 instead of 285.9. Well, if you got 252.7 points on a test that was possible 285.9, what's your grade? You divide what you got by what you should have got, right? Well, what you could have got, possibly. 252.7 grams divided by 285.9 grams, multiply times 100 to get a percent. Both of these are grams of Fe2O3, which of course will cancel. Fe2O3, Fe2O3. The grams cancel with grams up above, and we're left with a percent. Pretty good, 88.39. 88.39%. Very good. Number 3. More chemical engineering. Math is the engineer's great tool. Looking at the world around us and using math to predict and plan things and build things and engineer things. In this case, we're trying to manufacture a product. 47,000 metric tons of sulfuric acid are industrially produced every year in a U.S. state. How many moles are produced? 47,000 metric tons. How many moles? So the question is, how many moles of sulfuric acid? How many moles H2SO4? Let's write that under. How many moles of H2SO4? That's the question. Is 47,000 metric tons. MT for short. Metric tons. Well, a metric ton is 1,000 kilograms, it says. And we want to know how many moles. Oh, metric ton. Well, we can change that to kilograms then. It is the same substance, H2SO4. 1 metric ton would have to be on the bottom. Metric ton is 1,000 kilograms. We get rid of that unit. We want to know moles, though. Moles. Do we know? Could we put moles into the next factor? Well, not directly. We could, if we said change that to grams instead of kilograms. We know that there's 1,000 grams in a kilogram. We get rid of that unit label, and now we have grams, and we do know a conversion from grams to moles. For H2SO4, you would have to add up all those. The H2, that would be 1 times 2. The sulfur is 32. The oxygen is 16 times 4, that's 48. You add all those together, and you get 98 grams as a mole. If you want 4 significant figures, it would be 98.09 grams of sulfuric acid is a mole of H2SO4. Got rid of the unit grams of sulfuric acid, and we're left with moles. So how many moles would that be? 47,000 times 1,000 times 1,000, and then divide by 98.09. 4.8 times 10 to the 8th. Or if you didn't express it in scientific notation, it'd be 4.8 with 8 zeros afterwards. And the unit label is the only unit label we haven't factored out, moles. Wow, that's a bunch of moles. A mole is already a lot of molecules, unimaginable number. But now we're talking about that many moles, 10 to the 8th moles, nearly a billion. Flip my page over. What is number 5? Number 4, sorry. Number 4. What does it say? Write the net reaction for the production of sulfuric acid. Well, the net reaction. You take sulfur, and by the way, this happens even when we're not trying to manufacture it. It happens in nature. We burn gasoline that has some sulfur in it. We burn coal that has sulfur in it. Burning, of course, means combining with oxygen. One of the intermediary steps is it makes sulfur dioxide. That stuff that stinks when gunpowder is burned, the smell of gunpowder is sulfur and oxygen, making a compound called sulfur dioxide, or perhaps even sulfur trioxide, 3 oxygens. In the process of going up your nose, it actually mixes with the water in your nasal membranes and creates sulfuric acid in your nose. It can get in your lungs and create some sulfuric acid, and that makes you cough and makes you produce a lot of fluid to surround that so that you can isolate it, and it's a way of protecting yourself. But if you got too much of it, you could actually drown in your own lung fluid from breathing too much of this sulfur dioxide, sulfur trioxide gas. It is nasty stuff. But when it combines with water, whoops, I jumped a step. Here, we want to add water. in the process, and that's how we get the sulfuric acid. SO2 or SO3, if you can kind of see what's going on, if you get SO3 and H2O, now you have H2SO4, which is our final product, H2SO4. Now there's a lot of stuff missing from that reaction equation, right? Well, first of all, we'd have to say, well, this is a solid. We want to tell people this is a gas. We want to tell people this is a liquid. And we want to say this is a liquid, because that's what it produces at the end. But it's also got something else. It's not very useful equation for an engineer if we don't know the numbers. We got to have the numbers. We've got oxygens have to be balanced. That's the tricky part, because you've got to have 3 oxygen molecules to produce 2 sulfuric acid molecules. You can see that kind of working out with the oxygen. If we had 2 more oxygen here, you'd have to have 4 hydrogen on the left, 4 hydrogen on the right. We have 2 oxygen plus 6, that's 8 oxygen on the left. We have 8 oxygen on the right, 2 O4 groups. And whoops, we're still missing sulfur, right? We want 2 sulfurs on this side. Yeah, that would be, I think that's what they requested, net reaction for the production of sulfuric acid. It happens in the smokestacks of our coal-burning power plants. It happens in the tailpipe of your automobile. It happens every 4th of July when we burn gunpowder. And it goes up your nose. Number 5. About 60% of the sulfuric acid produced worldwide is used to produce phosphoric acid for fertilizers. The reaction is given if about 16,000 metric tons of phosphoric acid are produced every year in the United States. How many metric tons of sulfuric acid are required? There we go. Number 5. The production of phosphoric acid from this mineral is dug out of the ground, calcium fluorophosphate, and sulfuric acid. So they have to produce sulfuric acid to produce phosphoric acid. Well, phosphoric acid would be used in fertilizers, to make fertilizers rather. It's also put into some things for flavoring. Dr. Pepper has phosphoric acid in it. H3PO4. It's a preservative also in foods, and it has many, many other uses. H3PO4. Well, if 16,000 metric tons of phosphoric acid are produced every year, that means 16,000 here metric tons. What's the symbol for that? Metric tons. I guess they just use a little t, tons, but not 2,000 pounds like we use the word ton. Instead, it's a metric ton, which is 1,000 kilograms, or 10 to the 6th, a million grams. 1,000 grams is in a kilogram. 1,000 kilograms is in a metric ton. So 1,000 times 1,000 is a million. 10 to the 6th instead of 10 to the 3rd. So our question is, how many tons of this sulfuric acid will be needed? Yeah, you got to know your recipe. It's like baking cookies. You got to know how much flour and salt and whatever else. I just pour it out of a bag and make cookies. I had an egg and oil and water. The egg is an emulsifier, helps the oil and water stay together. The rest of the bag's already been measured for me. But anyway, you have to know that recipe to mix them together right and to get how much product that you're interested in. Engineers do this on a very large scale. How many? Well, let me write out the equation. Yeah, I don't want to get too far ahead of you, but here's what I've got so far. We're going to take up a part of another line. This is kind of a long factor label method. the first thing we do is change tons to grams. There are 10 to the 6th grams of phosphoric acid in a ton, metric ton, of phosphoric acid. So the question that we asked at the beginning here, how many tons of sulfuric acid will be needed to make 16,000 tons of phosphoric acid? When I know 10 to the 6th grams, million, grams of phosphoric acid is a ton of phosphoric acid, and then I know this too. These two are equal. 97.99 grams of phosphoric acid is a mole of phosphoric acid. I get that number from the periodic chart. 3 hydrogens, 1 phosphorus, 4 oxygen. Add them all together, 97.99 grams. Because in doing that, I have factored this label. I have factored the grams label. I have the mole of phosphoric acid left. Well, that's not what I'm asking for. I want to know how many tons of sulfuric acid. But my balanced equation up here tells me the ratio between sulfuric and phosphoric. I have 3 moles of phosphoric acid made for every 5 moles of sulfuric acid used. The unit label on the bottom has to be the one on the top from the step before. 3 moles of phosphoric acid are produced for every 5 moles of sulfuric acid used. There, at that point, moles of phosphoric acid cancels and I'm left with moles of sulfuric acid. But I want grams of sulfuric acid. Actually, I want tons of sulfuric acid. So I need to change moles of sulfuric acid to grams, which is kind of just the opposite of what we did here. We changed grams to moles by putting moles on top, grams on the bottom. But now we're going to put the grams on top and the moles on the bottom. A mole of sulfuric acid, H2SO4. How many grams is that? Grams H2SO4. How many grams is a mole of H2SO4? We had this in another problem earlier. What was it? 98.09. 98.09 grams of sulfuric acid. Now, if we stopped at that point, we factored out the label moles of sulfuric acid, but we're left with the unit label grams of sulfuric acid. If we put all those numbers in, our unit label would be grams of sulfuric acid. But we wanted to know tons of sulfuric acid, so we need to multiply one more step. Grams of sulfuric acid would be on the bottom. 10 to the 6th is a ton. So 10 to the 6th grams H2SO4 is a ton of H2SO4. There we go. Now we can put all those numbers in. The answer we get, 27,000 tons of sulfuric acid. That's how much you would have to use per state, they said, per year. In every U.S. state, yeah. We use a lot of sulfuric acid. By the way, we use phosphoric acid and sulfuric acid for manufacturing products like polymers and textiles and plastics and all kinds of things. So widely used manufacturing product. Number 6. The last 2 questions are not problem solving. They're not mathematical, and you may have your own answers. The exact answer is elusive. There's no exact answer, but this does hearken to the verse in Genesis that God tells us to subdue and take dominion over the earth. And when we can manufacture things safely and without causing pollution to the environment, then that is to our advantage, and that follows God's command. So, can you think of a way to reduce emissions from the contact process or to lower the cost of sulfuric acid production? Well, producing sulfuric acid, if you remember, it involved the use of sulfur, and it produced sulfur dioxide. So if you can minimize the need for sulfur, they used to get it out of the ground with hot water, and now they use it, they actually take H2S, which is a waste gas from the refining of petroleum, and you can get the sulfur out of that. So it's kind of like recycling. You know, we get the sulfur out of the H2S. This, by the way, smells like rotten eggs. It is. Some people think it smells like bad gas. Anyway, it's stinky stuff around oil refineries, but we can pull sulfur out of that, recycle stuff that we used to just throw away. That is conserving the environment. And of course, SO2 and SO3 gases are both toxic and so we want to contain those as best we can. We don't want those to escape into the environment. We want to contain them. We could say SO2, SO3, keep from losing them. Toxic gases. Some other ideas that you may have. The heat. What if you took, because this makes a lot of heat, could be used as an energy source, you know, to do something else with. Take the heat from chemical reactions and use them to do something else useful. Anyway, you might have some different answers. Let's look at number 7. What does it say? Since sulfuric acid is toxic and polluting, should Christians oppose its creation? Well, we could use the same argument with water. Water causes people to die. Water can cause burns if it's in the vapor state. Water composes 70% of cancer tumors. I mean, its responsible use is what God has asked us to do. I don't think he meant for Christians to. You can't avoid all chemicals. The food you eat are chemicals. So, but there are some chemicals that are more powerful. The more powerful for good, the more powerful for evil also. That's what kind of sums that up. Yeah, we want to use sulfuric acid responsibly. Of course, every time you start your car, you're depending on sulfuric acid to get your car started. That's a battery of your car. Depends on sulfuric acid. I think we should thank God for all of these things. Pause for a moment and we'll pray. God, thank you for giving us the mathematics to be able to predict things and calculate things so that we can take care of your earth. The nature that you have provided us. Let us be good stewards and to be responsible for toxic things, that we would use sulfuric acid and all these other chemicals in a way that brings your love to people. We can show them that you love them. In Jesus' name we pray. Amen.